We've spent this chapter talking about ethers, and now we're going to talk about a very specific class of ethers called epoxides. All right, and let's just remind ourselves what an epoxide is. An epoxide is any molecule that contains this pattern of atoms right here. A three-membered ring with an oxygen in that ring. It can have any number of carbons coming off of it. All right, this is kind of our simplest epoxide that we can have. But necessarily a three-membered ring. All right, and if you remember talking about cyclic alkanes, what do we know about these three-membered rings? Are they happy or unhappy? No, they're furious. All right, carbon really likes to have a bond angle of 109.5 degrees, and if you force it into a triangle here, it has a bond angle of 60 degrees, way less than its ideal bond angle. So these three-membered rings are unstable due to what we call ring strain, actually specifically angle strain. And so what makes these ethers are kind of boring, right? They don't really have very many reactions other than we can make them and break them. Okay, but our epoxides are going to be much more reactive because this ring is so unstable. And what we're going to see, all of our reactions of epoxides are what are called ring opening reactions. Okay, we talked a lot about reactions that occur under acidic conditions. Now we're going to talk about reactions that occur under basic conditions. We're going to look at some mechanisms of these epoxide reactions, and they're going to occur under basic conditions. So under basic conditions, we need no strong acids. If we have any strong acids, we know we've made an incorrect move in our mechanism. Okay, well, our base, if we need a proton acceptor, now we can use the hydroxide ion, our go-to base. This is perfectly acceptable under basic conditions. Okay. However, what if we need an acid for these basic conditions? What if we need something to be donating a proton? We can't have any strong acids, but we can have other weaker acids. And so if we do need anything to play the role of a proton acceptor, we can just use water. All right, so under acidic conditions, it was hydronium and water as a base. Under basic conditions, we can use hydroxide, and so water will be playing the role of an acid. Okay, and this is if we need any proton transfer steps. Generally speaking, basic mechanisms are a little bit simpler than acidic mechanisms. You usually don't need quite as many proton transfer steps to manage your charges. All right. And we say no strong acids, but let's just take a look at some of our strong acids and see if we can't figure out any sort of common structural features. So the most common strong acid that we refer to would be the hydronium ion. Okay, likewise, if we take an alcohol and we were to protonate it, that is a strong acid. All right, and so what do these strong acids have in common charge-wise? These positive charges. So similarly, when we say no strong acids, we could kind of simplify that down or give it a code for something that's a little bit easier to look for. which is no positive charges. All right, so when we do our mechanism, we want to make sure that we don't have any intermediates that have any positive charges. If we do, we're missing some sort of a proton transfer step to help us manage those charges. Okay, so let's take a look at our simple epoxide. Okay, so what we know about our oxygen is that it's fairly electronegative compared to carbon. So in this bond here, we're going to have this partial negative charge on our oxygen and a partial positive charge on that carbon. All right, so that carbon is cold, glowing blue with that partial positive charge, and that oxygen is red hot here. Okay, so now we're going to take our nucleophile. We'll use a simple nucleophile. Our hydroxide ion. All right. Now with ethers, we also have that same sort of partial positive charge on our carbon and partial negative charge on our oxygen, but they're not as reactive towards nucleophiles. If you just throw hydroxide in there, you don't have any sort of a reaction. Well, why? Because not only is this carbon got that partial positive charge, but if I form this bond right here, I got too many bonds on that carbon, right? So something's got to give. Well, again, this epoxide really wants to pop open. It's super mad being in this triangle form right here. So it's kind of got this built-in leaving group pair of electrons that is immediately going to be like, oh, thank God. Let's get rid of this triangle shape here. And so we're going to get this ring opening step right here where that pair of electrons jumps onto that more electronegative oxygen atom. All right? So everybody take a second, draw me the product of this step in our mechanism here. All right, so we have that carbon that now has that new OH group, and now my ring is open. And when that oxygen has accepted that extra pair of electrons, it has this negative charge. All right, so first of all, let's stop. Is this allowed to be here in our basic mechanism? Did I make any illegal moves here? No, because I have this. This is a strong base, but this is basic conditions. I'm allowed to have alkoxide. I'm allowed to have negative charges under basic conditions. Not under acidic conditions, this would be illegal, but under basic conditions, this is perfectly fine. Okay, so then the last step, we're not going to stop here. The last step will be to protonate that alkoxide ion. We're going to end up forming a diol in this case. All right, everybody take a second. Given what we discussed about these basic conditions here, see if you can't finish off this mechanism. We're going to need a proton donor of sorts. What should we be using? So what's my proton donor? Water. Pair of electrons, going to grab that hydrogen. Cool. All right, let's do one more real quick because I want to make a note here. We said that our base is hydroxide and our acid is water. This is kind of a good default go-to if there's not much other information, but it's really going to depend on our conditions, okay? So let me show you what I mean by that. We're now going to take an epoxide. Let's take a little bit more complicated of an epoxide here. And now we want to use a different a different nucleophile. Let's use an alkoxide ion. Also a nice basic nucleophile here. Okay, well, I don't want to mix my alkoxide ion with an aqueous solution. All right, that's because our alkoxide ion would simply react with that water to make hydroxide and an alcohol. And holy crap, is that an expensive way to make hydroxide. All right, if I wanted hydroxide, I could purchase sodium hydroxide for way cheaper than I could these alkoxides, right? So instead, whenever we use an alkoxide ion, we always use it in a solvent that is its matching alcohol. Because now if we have any sort of a proton transfer reaction, all we've done is create a new alkoxide ion, right? We're not ruining our supply of ions in that mixture as long as we use a matching alcohol, okay? So our good default for base and acid would be hydroxide and water, but specifically if we're using some sort of an alkoxide ion, we don't want to use water as our acid. We want to use that matching protonated form of that nucleophile. All right, so for our if we're using a specific nucleophile, for our acid, we want to use that protonated nucleophile. Otherwise, we could run the risk of just creating a basic solution. Okay, I want you guys to try to do this one on your own, but there's one more thing we're going to talk about to consider here. With all of that discussion of our ethers and kind of what you saw on your daily quiz, right? There's all of this like, well, which side is it going to attack? Okay, we have the same kind of problem here. I have this nucleophile, and really there are two carbons that are attached to that electronegative oxygen. Previously, it wouldn't have mattered what side I attacked. I use a symmetric epoxide. But here I would get a different product if my nucleophile attacks this carbon than I would if my nucleophile attacks this carbon. All right, so I want you guys to try to finish off this mechanism here, but I'm going to tell you there's not a mixture of these two products, there's only one, and I want you to think about which one of these two carbons is more likely to get attacked by that nucleophile. All right, what do we think, red or green? Right, and maybe I gave it away because I prefer red for my electron pushing arrows, but yes, we're going to use the red path. And why red over green? Simply more accessible. Which one can the nucleophile get to easier? It's going to have a more easy time getting to that accessible carbon with the red arrow than it is with the green. And remember, I'm not done with just that one arrow. We got to show our ring opening, the basis of these epoxide reactions, that ring opening step right there. Kind of going to draw this a little weird just to kind of make it clear. And let me color this atom a different color. All right, so on my carbon that got attacked, now I have my nucleophile, my new bond that's formed. And what's sitting over there on my orange carbon is that oxygen that was originally my epoxide oxygen. But when that ring opens, it opens up as this alkoxide ion. And in this case, what should I use to protonate that epoxide ion, that alkoxide ion rather? Ethanol, right? We don't want to use our alkoxide with water. We're going to use ethanol as our proton donor. All right, so we have these nucleophilic addition reactions here. We're adding our nucleophile to our epoxide. All right, and let's just lay out kind of our generic we have our epoxide. We add in some nucleophile. We get our nucleophile on one carbon. I guess we can say we got to follow it up with some source of proton there. Okay, and what we kind of just want to note here is there's a certain signature of a reaction that starts with an epoxide. We're always going to get an alcohol product, right? Because we have that oxygen in our epoxide that's going to get protonated, all right? But importantly, there's always this perfect spacing that we're going to see with these ring opening reactions, where our nucleophile gets added exactly 2 carbons away from where that alcohol group is. Right? And again, that's because of that ring opening reaction. Wherever the nucleophile attacks, that's where that ring is going to open up. So I guess let's just note here. Nucleophile added. And then the other thing that we discussed was what we would call regioselectivity of these reactions. By regioselectivity, I mean what do we say was our logic here behind which carbon is going to be attacked, which region our nucleophile is going to be added to? The more accessible, right? So more accessible means that that's where our nucleophile gets attacked. Now, when we do our regioselectivity, when we make our notes here, we're going to first say that under basic conditions, and we're going to note that our more accessible primary carbons will be preferred over secondary carbons, over those least accessible tertiary carbons. All right, and I'm going to leave a little room here under this regioselectivity section because I'm going to complicate things by now talking about these same reactions under acidic conditions. So epoxides, being the super reactive ethers that they are, we can have reactions that occur under basic conditions, or we can have reactions that occur under acidic conditions. All right, so let's note we've talked about acidic conditions before. Can't have any strong bases. Okay, this is going to be important for thinking about your nucleophile choice under acidic conditions. I can't use a hydroxide ion as my nucleophile under basic conditions, right? I can't use an alkoxide ion. So what we're going to see are our neutral nucleophiles, with the exception of those 3 halide ions that are great nucleophiles but crappy bases. You can have chloride, bromide, or iodide as well. All right, these would be acceptable under basic conditions. Our neutral nucleophiles are weaker nucleophiles, but what we're going to see in our mechanism is we got this first step that's going to make that epoxide an even better, make that carbon on that epoxide an even better electrophile. All right, and as we said, if we need an acid under acidic conditions, we can kind of default to hydronium. If there's something specified like HBr or HCl, you could use either. And if we need a base, what do we use? Water. All right, so let's just take our simple epoxide here. Okay, and I am going to react that with that neutral nucleophile water. All right, under these acidic conditions. I'm going to tell you that our product is exactly what we got under basic conditions using hydroxide, that diol. All right, so now you know where we came from and where we're going. And I want you all to see if you can't devise a mechanism here to get from A to B that respects our acidic conditions, what's allowed and what's not allowed to happen under acidic conditions. And again, if you make a mistake and you're like, oh crap, I have this negative charge I'm not allowed to have. Remember, you can mitigate that by doing a proton transfer step. Use those proton transfer steps to manage your charges. All right? But take a minute, just given what we've discussed for the past week or so, see if you can't devise a plan to get from A to B here. I'm just curious, does anybody feel like they have it? Okay. All right, so first of all, the whole point being like go in there, just try something out, see, make some mistakes, get to the next intermediate, say, all right, does this make any sense? Whatever. If you're really just super lost with these mechanisms, then you want to go back to those introductory assignments that we laid out. Make sure that you can follow these arrows. And that given just 2 steps, you can fill in those arrows, right? This is filling in 2 or 3 steps here, so that might be a little bit of a challenge. But it shouldn't be just like, but like again, if you're completely lost on these arrows, you kind of need to rewind back to the beginning of the semester where we laid out those introductory assignments. Did you have a question?
Yeah, would we start off with the base under acidic conditions or the actual acid?
Would you?
You have it as H2O up there.
So this is going to be my nucleophile.
Yeah.
Right? So this is what I'm adding to here. It's not going to be a base because there's no hydrogen that it's going to be removing, but it is also my base in my reaction here, okay? So kind of my goal of the logic that you might have gone through is, all right, I'm going to do exactly what we did before, and I'm going to have that nucleophile attack that carbon, that electrophilic carbon, right? Cool. Nucleophile attacks, that ring opens. If we did that step, just following our arrows here, this is what we'd have. And I look at this and I say, is this good or bad? I say, oh crap, I can't have that epoxide or that alkoxide ion in there. I can't have that negative charge. That's too strong of a base. But again, how do we manage that? How do we get rid of that? Let's just do a proton transfer step first. So just like we saw with our reactions of ethers under acidic conditions, my first step is not going to be a nucleophilic attack. I'm going to use that trick where we protonate that oxygen. So now I'm going to use that acid and I'm going to protonate that oxygen. And as I said, this is going to help us manage our charges because now if I do my nucleophilic attack, now when that ring opens, it doesn't open with an alkoxide ion, it opens with a neutral hydroxyl group. And that is perfectly legal under acidic conditions. Now again, these acidic mechanisms, you usually have a few more steps here because I still have to do yet another proton transfer step, right? When water joins, it joins, and now my oxygen has that positive charge. Now I gotta get to from A to B here. So now I need a base. Now I need a proton removed. And again, under acidic conditions, we can use water. Okay, so again, this first step here, we had to do a proton transfer before our nucleophilic attack. And we did that strictly, that proton transfer, to manage our charges. Okay? Now, water is a much weaker nucleophile than that hydroxide ion was. But importantly, when you protonate that oxygen, now it's going to pull the electron density away from that carbon even more because it's really mad to have that partial positive charge. Okay? So let's just kind of note, if we take a regular epoxide, compared to a protonated epoxide. Whoops, not two lone pairs. This carbon right here is an electrophile or an electrophilic site. But this carbon over here is just an even better electrophile, even more electron deficient. Which is why we can use our weaker nucleophiles under the acidic conditions. All right, so this is why it's okay to use a weaker nucleophile under acidic conditions. All right, so I want you all to do one on your own here. Try to use a different epoxide. We see what they look like here. All right, so first of all, HCl, does that mean I'm under acidic or basic conditions? Definitely acidic conditions. So in order to manage my charges, I'm going to have to do a proton transfer step. You can use hydronium. There's definitely hydronium in this solution as well, just for the sake of simplicity. My HCl is right there. I'm going to use that. So now I have this protonated alkoxide. And now that carbon is an even better nucleophile. Chloride's pretty decent, or even better electrophile, excuse me. I guess let me swing it around to this side to match my products. And again, I have to show that ring opening as well, right? The key to these reactions being that ring opening step for our epoxide. All right. And because I use that chloride ion, I don't have one extra proton transfer step to occur here. We're good here. All right, with your neutral nucleophiles, you have to have that extra proton transfer step to get rid of that hydrogen. Chloride's one of those rare negative nucleophiles that can exist under acidic conditions. And so I don't have that extra proton transfer step at the end there. Okay? So now, again, let me just real quick implore you guys, if you guys are sort of feeling about your mechanisms, just go back and practice some of those old assignments. You can practice any past due assignment. The very beginning of the semester, there were specifically mechanism-based assignments, electron pushing arrow assignments. Just make sure that you're comfortable with those. I know, like, especially, like, some people are like, oh, screw it, I'm just going to memorize these things, right? That's great when there's, like, 2 or 3 of them. You're going to reach a critical mass where the idea that you're just going to memorize every mechanism out there is going to fail, right? So you really want to understand what's going on so you can build these yourselves. All right? One more complication to throw, which is our regioselectivity under acidic conditions here, okay? For basic conditions, it was a very simple accessibility argument. Under acidic conditions, that's part of it. Certainly primary are preferred over secondary. But it turns out that there's something magical about a tertiary carbon under acidic conditions, which makes that even more preferable to nucleophilic attack. All right, so let's take an epoxide. Okay. And we're going to put a tertiary carbon on one side. That tertiary carbon is very, very crowded, right? Very hard for that nucleophile to get to. But under acidic conditions, we protonate that oxygen. So that when that ring opens, it doesn't open as an alkoxide ion, but it opens as a neutral hydroxyl group. All right, and like we said, when that happens, that oxygen, now it's all mad because it's got that formal charge of +1. So it's going to do an even better job of stealing electron density away from those carbon atoms. All right? And if you have a tertiary carbon, tertiary carbons form quite stable carbocations. And so what's going to happen here is you form this intermediate where this bond kind of starts to break a little bit already. You don't form a full carbocation, okay? But what you do form is this sort of lopsided transition state kind of thing. This is how they picture it. where that bond is sort of well on its way to breaking already. It's already mad that it's in this massively angle-strained configuration here. All right, so because that carbon is kind of happy with the positive charge, that epoxide starts to open up already before the nucleophile has even had a chance to attack. All right, so let's just note here, because tertiary carbons form stable carbocations, with that ring strain, with that angle strain, that ring opening reaction begins. Before our nucleophile even attacks. So that's why under acidic conditions, if we have a tertiary carbon, that's actually going to be preferred for nucleophilic attack. And then if we're comparing primary and secondary, it's just an accessibility argument, right? Neither of those form terribly stable carbocations, so then we're just going to have a which easier to attack kind of argument going on. So let's just do two examples side by side that illustrate this. We're going to take an epoxide with a secondary carbon, react it with one of our neutral acidic nucleophiles, water, let's use an alcohol just so we can make it more clear which way our ring is opening up. Okay, and what we're going to see is that our nucleophile is going to attack that more accessible carbon. And thus my hydroxyl group for my ring opening is on that less accessible, more substituted carbon. All right, but if we do the exact same thing, but this time with a tertiary epoxide, we're going to see that our nucleophile actually attacks that tertiary carbon and our hydroxyl group is on that primary carbon. I guess just to make this extra clear, I'll color my epoxide oxygen and my reactant and my product. We'd be good and put in lone pairs. Compared to where my nucleophile's oxygen went. So primary over secondary, but tertiary wins over everything else. Right. Cool. All right. Enjoy your weekend. We will be back here next week for, I don't even remember, review, I guess, mostly.